We then need to contact them, right? That's not so easy. Again, you have something that's nanometers in diameter. It's only a few micrometers long. How do you put your probes on it to measure the conductance? What I really want to do is take one of these, a fluke, a multimeter, and just put the probes in the nanotube and measure it, right? But you can't do that. So how do I make contacts that are big enough that I can put the probes on it? And here we use what's called lithography. And that's just a process of using sort of a photosensitive, it's like photography. Use a photosensitive material, put a mask on it. You use light, which has very small wavelength, right? So you can make a really small gap based on your light. Okay, so you radiate it, you expose a little area, you develop it, that little area gets exposed, you backfill it with metal, then you lift off the photosensitive material, you're left with a little tiny patch of your metal in a really small area that you've designed. Okay, and you can see here, this metal, here's our metal that we patterned on the surface using this process. This length scale is 5 micrometers about, and here you can see a nanotube with the contacts on it. Okay, so if you use optical lithography using light, you get about 1 micron feature sizes. With electron beams to expose, you get things down to 10 nanometers. We use electron beam lithography a lot to contact these things on such a small scale. It's actually a very laborious process. Okay, you can see here, here's what the devices end up looking like. Here's our nanotubes. We contact these, and then we go out to something that's bigger, and here is something that's a millimeter in diameter, in length, and we can actually just contact this pretty easily. Okay. So it's amazing that we can actually measure conductance on things that small just by scaling up to bigger sizes. And this process might take 10 days of work or something, actually, just doing all the different steps. At the end of the day, you can measure something that's really tiny, which is neat. Now, some of this has been done, just making the tube devices are things that people did before I started researching. So, if you want to research, you have to do something new. So one of the things that I've been working a lot on is making more different sorts of contacts and gates and getting local control of these nanostructures. And so I spent a lot of my postdoc time and time at Illinois trying to take nanotubes that are contacted and put more gates on them. And this is tricky because usually they're so small that they get damaged when you put things on them or near them. So we developed ways to put a small insulating layer over the tube and then align more local gates, we called it, for sort of local probes and local control. Here's gates on top of the tubes. Here's the tube here, and these are gates next to the tube. And this is where we have gates underneath the tube. And we put an insulator between the tube and the gates so we can have layer by layer control of the barrier. So if we put a very thin insulator, we can have something that's pretty well conducting to the tube, maybe a tunnel contact. If we put a very thick barrier, we have a gate where it's just electrostat capacitively coupled. Other things that we've done is use an atomic force microscope tip to actually bend the nanotube. Again, you literally take this tip, drag it across the nanotube, and make it bend. And here's some bends we've made in nanotubes themselves. And I'll show later that this changes the conductance of the tube. We can measure that. Okay, and then sometimes we line these top gates over the bends, right? Combine everything we can do to make something new. So here's nanotubes where we've actually put the gates over where the bend is and away from it. Here's a double bent tube with 2 gates over there. So we work a lot to make things that are a little bit different, to try to use these local probes to get some local control over the nanotube properties. And we also generally measure at low temperatures. And we're interested in quantum properties. You don't see quantum properties at room temperature because at high temperatures, all you see are temperature effects. Right? Those are much higher energy scale than quantum effects. So we have to cool things down to near 0 degrees Kelvin, just near 0 degrees in general, any scale, to get the quantum properties. We use specialized refrigerators and cryostats to get these things down to very low temperatures. Okay, and again, the things we're looking at are, what happens when we have small dimensions? Can we see and study quantum properties? And can we make novel ultra-small devices? Okay, so here's a nanotube device. These are very simple measurements in a sense, right? The real difficulty is in making these things and getting the fabrication and making something new. Then I tend to do pretty simple measurements. Alternatively, you could have a very simple device and make very hard measurements. You probably don't want to have a hard device and a hard measurement because you'll never get anything done. So I've chosen to take a simple measurement, right? So what we do is we take our nanotube, treat our nanotube as a resistor, put a voltage across it, measure the current. 2-terminal device, very simple. A little bit more complicated sometimes. Here's our nanotube, have 2 contacts at the end, put a voltage across it, measure the current. Sometimes we have a capacitively coupled gate that can also affect it. Okay, so you'll see things as a function of what I call the gate voltage. That's just this, it tunes some of the energies in the nanotube as well. Here's a false color image. The back gate is usually just a doped wafer that we place it on. There's an oxide layer to insulate it, and then here's a nanotube in false color red and 2 contacts. A standard device, and again, sometimes you put other gates on it too. This is the standard measurement though. And what do we see if we just measure a simple nanotube? Let's just, forget gates, forget anything. Let's just measure this device, Put it, measure this with a back gate, end-to-end conductance. What do we see? It turns out even that is pretty interesting, right? So here's the conductance of the nanotube, or the current related to conductance, versus this back gate, this capacitively coupled gate. And if you just follow this room temperature, I don't have the temperatures, this is a room temperature line, the red, you see that it's 0, 0, 0 conductance, and then it turns on. And then you go back, and it's high conductance, and then it turns off. It's a MOSFET, right? That's a transistor. With a voltage, you can turn it on and off. So even a simple nanotube device with just a gate voltage is an ultra small transistor. And people have worked to make these even better and found that they have better switching ratios than even silicon. Okay. Now, they haven't replaced silicon because they're just hard to get to where you want them right now. But in terms of physical properties, they're really amazing, even as just this simple sort of thing. So already, just in the very simple nanotube device, it's just a novel, ultra small thing. And you can see here, this is room temperature. You get much better properties in the blue and the green as you go to lower temperatures. This is 4 Kelvin. Now, you might notice something else here. There's some wiggles on this. Okay, you think, well, okay, your data went bad all of a sudden, right? I went to even lower temperature, and now the data is even worse than it was before. It turns out these wiggles aren't bad data. There's something even more interesting that happens in these things. So, here's higher temperature, and then I think this is 70 Kelvin. And as you go to 4 Kelvin, you see something else. It turns out this is Fabry-Perot interference. You guys heard of Fabry-Perot cavities? Some of you have, right? So the Fabry-Perot cavity is common in optics, right? It's just typically in optics, you can put 2 mirrors at either side, and you can put a photon in there, and it can resonate back and forth between the 2 mirrors. You can see interference between the waves. Okay? Turns out the same thing happens with electrons in a nanotube. In a nanotube, you get nearly perfect conduction. They call it ballistic conduction. It doesn't hit anything along the way, right? Because it's this perfect crystal, right? The electrons are just going around the outside of this perfect carbon crystal, so it just goes from one end to the other without hitting anything, without losing any of its properties, of any of its phase. So it turns out an electron can go into a nanotube and bounce back and forth. And because an electron is also a wave, and because these things are so small that you can see quantum properties, the forward and backward paths of the electron can interfere with each other. You get a standing wave pattern inside the nanotube, right? But it's an electronic standing wave, not a photon. It's an electron standing wave inside this thing. And those are those wiggles that we're seeing. And you can see it, if you look at it a little bit differently, this is a 2D conductance plot where the black is low conductance, the white is high conductance, and we're looking as a function of this back gate and our end-to-end bias. And it turns out we see these oscillations because the electron wave numbers are changing as we shift the energy with the source drain bias, and as we shift the wave number with the back gate. And so we're shifting the phase of this electron wave as a function of source drain and back gate. And you can see this interference pattern. If you can you see sort of a pattern there? You don't believe me? Pattern? Yeah. It's not beautiful because it's a nanotube and an electron. It's not a photon and a cavity. But I guarantee it's a pattern that's been shown really beautifully by other people. This is not as beautiful data we've taken, but it's clearly an interference pattern that you can see here, which I found pretty neat. I was pretty excited to see that because it's 1D behavior, right? It's back and forth interference, and it's quantum, fundamentally quantum, in a thing that we're just probing with our wires. Okay, so let's make more devices. What happens now if we bend a tube and just put a gate over it? So here we have a nanotube. We've put one of these local gates on top, and we've bent the tube. So we have gates over where it's bent and gates over not where it's bent. Here it turns out we can see preferential conductance through the bend. So we can choose a tube in some regime where it's not very well conducting outside from the bend. So if we measure conductance as we put voltages on the green and the blue probes, we see very little conductance. It's 0, but it's basically flat. Not much happens.